disappointed in myself. So today is April 1st. We're just going to talk about the physical characteristics of gases. So we're not going to talk a lot here about how they react with one another chemically. That's the next chapter. And I've sort of stacked these slides because this is these two slides. Kinetic molecular theory of matter is a term you probably have not heard, but you know what this is. This underlies everything you know about matter. You have been learning the kinetic molecular theory of matter from the first moment you did science about matter in any science class, somewhere in middle school. Nobody ever called it this before, but you've been learning this. So you all take for granted that all matter is made of little tiny pieces that vibrate, yes? And that the hotter they get, the faster they vibrate, yes? That's kinetic molecular theory of matter. That's all it is. So you now have the official scientific handle for what it is. This is a scientific theory just like the theory of gravitational attraction or the theory of biological evolution or anything else. Very well understood, very well supported. No reliable and repeatable observations counter this idea. So all the evidence that we can gather says, yes, all matter is made of tiny little pieces that vibrate. The hotter they get, the faster they vibrate. The colder they get, the slower they vibrate. And everything that we can observe about matter fits with that. So it's a theory. Within what we're going to call KM, kinetic molecular theory, this idea of an ideal gas is one that we're going to work with because we'll get to the ideal gas law in chapter 11. The ideal gas is kind of like the ideal child or the ideal dog or the ideal sibling or the ideal best friend. It behaves perfectly every single time, even when no one's watching. You think the odds of that are slim. But we pretend that gases behave ideally. So we pretend that gases behave in this absolutely perfectly ideal fashion in order to talk about them mathematically. They don't. I'm going to be honest with you. Just, the ideal teenager. Lots of you are awesome teenagers. You're great people. But you're not perfect. Nobody is. You're figuring this out as you go. Gases are not ideal either. But in order to talk about their overall behavior, we treat them as if they were. What we claim is that they behave just the way we expect a gas to, that there are no deviations from this expected behavior, and there are 5 assumptions that we use to talk about this. I have got all 5 of these on one slide, so we're just going to run through these really quickly, and most of this you know. So the first one is, and this is pretty true, these vary from a little bit of a stretch to pretty close to the truth. Gases consist of particles that are very far apart from one another. Okay, I would like all of you to take your hands, put them up in front of you, and do this. With enthusiasm, come on. Okay, that's beautiful. I wish I had video. You're not playing along, Mr. Johnston. What are you hitting?
Air particles.
You're hitting gas particles. You're hitting oxygen, CO2, maybe little bits of argon here and there, lots and lots and lots of nitrogen particles, N2 particles. If you do the same thing on your desk, is it going to feel different on your hand? Yes. Because the desk is made of particles that are a lot closer together. The particles in your desk are not as free to move. Your hand doesn't go through those particles and move them aside. When you smack the air, those particles are far enough apart. The ones that you hit, a lot of them just move out of the way. You create a breeze by moving those air particles out of the way. So the first assumption, and this is pretty close to truth, is that gases, lots of particles, but they're really, really spread out. They have a low density, and that there's a lot of empty space in any gas. There is a lot of empty space in the sort of soup of gases that you are sitting in. Lots of space between the particles. That's why we can compress a gas. You have all compressed a gas if you've ever used a hand pump to pump up a bike tire or a basketball or a tractor tire or anything else. You have compressed a gas. You have put it under pressure in a cylinder and put it into a vessel. Okay, that's number one. On the truth meter, yeah, I'd say 99% true. That's how they behave. The second assumption, collisions between gas particles and containers and other gas particles. Basically, when gas particles run into things, they bounce right back. There's no loss of kinetic energy. So, you know what kinetic energy is. It's the energy of an object in motion. And if you take two bowling balls and roll them towards one another, they each have kinetic energy. When they smack together, they'll roll, this is like playing pool, they'll roll in opposite directions. But each of them will lose a little bit of energy. And they lose it to vibrations, to surfaces, to friction on one another. There are all kinds of reasons that objects lose a little bit of energy. It gets lost out to the environment. We pretend that when gas particles strike one another, that doesn't happen. Well, from a physics perspective, straight up, it does. It's a lie. But, you know, truth meter, 75, 50, I don't know. I'm not enough of a particle physicist to assess the real truth of that statement. But the loss is pretty minimal because these are pretty tiny particles. So we can basically fudge the numbers and say, yeah, there's no loss of kinetic energy. Nothing to see here, folks. Keep moving. So that one's shaky. We'll do that. Number 3, which really should come before 2, gas particles are in continuous, rapid, random motion and therefore have kinetic energy. Truth meter says absolutely, yeah. You know, if there's any part of that that's not true, I don't even know what it is. So yes, just like all other particles in the world, matter's made of little particles that are moving around, and because they're moving, they have kinetic energy. Okay, 4, this one is not true. It's, I don't know, 50 to 75% true. Again, not enough of a particle physicist to really assess it better than that. There are no forces of attraction or repulsion between gas particles. Well, that's not true. You haven't done gravitational attraction. I don't think you do that in physical science. Any two things that have mass have an attraction for one another. The bigger the mass, the stronger the attraction. The smaller the mass, the smaller the attraction. We are all strongly attracted to the Earth because the Earth is massive. If you're standing a centimeter away from your friend, your masses are attracted to one another. Whoa, dude. We can't feel that because the attractive forces from the Earth are so huge. They overwhelm all those little micro-attractive forces. If I stuck the two of you in space and stuck you a few inches apart or a few centimeters apart, you would start to move together. If you were outside the field of influence of the gravity of a planet or an asteroid or a moon, you would start to move towards other masses. So of course there are some forces of attraction between gas particles. And we'll talk more later about some of the other little exceptions to that. So this one's shaky at best. Number 5, this is pretty true. The average kinetic energy of gas particles is dependent on their temperature. So, we said the hotter we get something, the faster it vibrates. Heating something up is just making its particles move faster. And we can actually figure out kinetic energy for an individual particle. We'll do this a little bit in the next chapter. It's terrible. Don't worry about it. You're not there yet. So we have an equation that you may or may not remember from physical science. Kinetic energy is equal to 1/2 mass times velocity squared. You don't need to know that for here. But the big thing is that because particles at the same, any two particles that are the same temperature have the same velocity. All temperature is a proxy for velocity. It's a way of measuring velocity by proxy. If you have a cement block and a ping pong ball, and they are moving at the same velocity, one of them has more kinetic energy. Which one? The one with more mass, yeah. the cement block. If I was going to get smacked by one of them, I'd rather get smacked by the ping pong ball, not the cement block. I don't want to be smacked by the cement block. So if we have two things that have the same kinetic energy, but therefore have the same velocities, have different masses, the heavier one moves slower. Okay? Lighter, Honda Civic full of cotton balls, semi-truck full of cement blocks.
Wow.
Seriously. Differences in magnitude and of mass. The heavier thing will move more slowly. The heavier thing will move more slowly. So at the same temperature, heavy particles move more slowly, lighter ones move faster. That's it. And that one's pretty true. There's not a whole lot of fudge in that. So there are really only two of these assumptions that are a little bit fudgy. Okay, that was a really high-speed tour through sort of the things that underlie how we talk about ideal gases. Questions, comments, or concerns? So we're going to talk a little bit about what kinetic molecular theory means and how gases behave. Most of these are such no-brainers that you read them when you were doing your close reading and you went, well, yeah, duh. Oh, yeah, duh. Gases fill their container. They don't have a definite shape or a definite volume. They will expand to fill the container they are in. The definition of a fluid is a state of matter in which the particles can slide past one another. So there are two states of matter which are considered fluids, liquids and gases. These are both fluids. If you end up in an engineering program, there's a whole branch of engineering called fluid dynamics, and it models how fluids behave, used for both gases and liquids, used a lot in stream design stuff. So those are 2 points, and that's because kinetic molecular theory says all matter is made up of little particles that are vibrating. So that allows for these characteristics of gases. Gases are not very dense. Gases can be compressed. Okay, again, you read those when you did your close reading and went, yeah, duh, right? Okay. Here are the two that you may not have felt so blasé about, diffusion and effusion. So, if I spray perfume in that corner of the room, initially, who's going to smell it first? Well, I am. I sprayed it. Who's going to smell it next? Andrew and Tarek and Adam. Who's going to smell it last? David and Robbie and Sarah. So what we're looking at, and I'll jot over to this blank slide here, is that for any fluid, if we have an area of high concentration of something, so this could be a container of gas, I could make this a liquid, whatever, all particles move from areas of high concentration out to areas of low concentration until they're evenly distributed. So that perfume odor that was really, really strong over here, by the time we spread it out to the whole room, you might not smell it at all, because the number of odor particles per snoutful of air you could take in would be pretty small, and it would be very, very dilute. You wouldn't get a strong odor, okay? This idea that any kind of fluid particle moves from an area of high concentration to low concentration is called diffusion, okay? And if you've done anatomy and physiology, or if you remember back to biology, we talk a lot in biology about diffusion of liquids into and out of cells. When gases diffuse, so they mix randomly, and that's part of kinetic molecular theory, that these little particles are in random motion. But how fast they diffuse depends on the speed of the particles. That's the single biggest controller of how fast they move. Well, what governs how fast they move? Temperature, but at the same temperature, it's all about mass. So heavier particles move more slowly. Semi-trucks full of cinder blocks move more slowly than Civics full of cotton balls. And if we have heavy and light particles, the lighter particles will reach that end of the room faster than the heavier particles will. the upshot of that is that light gases diffuse more rapidly than heavier ones. Okay, so if you have methane, natural gas, if you have they attach a smelly part to it. It's called a mercaptan, because natural gas is odorless. It'll kill you, but it's odorless. So they insert an odor particles, an odor component into natural gas. They do the same for propane. It's a different smell, and those odor particles travel with the natural gas. Now, in order to get them to travel at close to the same rate as the natural gas, what would you have to make sure was the case? Similar in mass. That they're similar in mass. Because if all your odor particles are very, very heavy, but your natural gas is very light, guess what? You could have natural gas reaching that end of the room in good concentration and have all your odor particles still be back here. So people back here are saying, I smell a gas leak. And people there are like, I don't smell anything. Right before they pass out and die. So the mass of the particles governs how quickly they diffuse. That's diffusion. Effusion is a slightly different concept. So we have diffusion and we have effusion. And effusion is very specific. It is moving particles through a small opening. So balloons effuse. How many of you have ever had a balloon? Nice little old latex balloon. We get one every time we go to the grocery store, because they give them out free at the grocery store I go to. It's a big hit. Do they look the same 2 days later? No. Because that latex surface of the balloon, Cooper, is full of little tiny holes. They're too small for you to see, but they're large enough that those gases can travel in and out of them. And so those gases effuse through the holes. Now, do different gases effuse at different rates? What do you think governs that? Speed and therefore mass. I mean, as long as the molecule can fit out of the hole. So again, rates of effusion directly proportional to velocity. Velocity is directly tied to mass. So that's sort of the 4 points of how they behave. They expand, they're fluids, they are low density, therefore compressible. They diffuse, they effuse, and those things are tied to how big they are. Real gases, like real teenagers, real pets, real best friends, real everything, doesn't actually behave ideally. This is the truth. Nothing is ideal. Real gases don't completely follow the rules. They don't completely follow the way we would predict they would behave in kinetic molecular theory. So, in the 1870s, and you're going to want to say this with me, it's fun, Van der Waals. It looks like Van der Waals, but it's Dutch, so it's Van, because the V has an F sound, and the V, or the W has a distinct V sound, so that's Van der Waals. Isn't that fun? Don't you want to say that repeatedly? Go ahead. 1, 2, 3. Van der Waals. There you go. You'll feel better all day. So Van der Waals was a chemist, physicist. I think the line was blurry at that point. And he noticed that there was actually a deviation from ideal gas behavior, and he attributed this to little attractive forces between particles. That there were, in fact, little particle attractions that went on. We see that mostly when things are at high pressure. Well, what does high pressure do? It pushes stuff together. Put a gas under high pressure, you're pushing those molecules really close together. Well, the closer you push them, the more, if there are any little tiny attractive forces, the more those are going to show up. So very high pressures and very low temperatures. If they're at a high temperature, they're moving fast past one another. They don't have time to hook onto one another. At low temperature and high pressure, they're very close and very slow. And that's where there's actually a chance for them to go, hey, buddy. And create that attractive force between them. So that's where we see these deviations most. The ideal gas thing, most of it's true if we're talking about something like a noble gas. Something where there really are very, very, very little in the way of attractive forces, and they're not at crazy, crazy high pressure or crazy, crazy low temperature. So at pretty much normal conditions, in something that doesn't have a lot of force, that's where we're pretty spot on with the kinetic molecular theory and with an ideal gas. Okay? When you talk about a gas, under any conditions, you have to specify some of the physical conditions that that gas is under. And we talk about gas volume and gas temperature, and you know how to calculate number of molecules. Pressure is the thing that we haven't talked about yet. Pressure is not force. Pressure is force per unit area. So pressure is equal to the force divided by the surface area over which that force is applied. And right now, what I want to know is if you feel like you're under pressure. Anybody feel a crushing weight of pressure? What, 10 miles of atmosphere? Gases have masses, you know. Gases have masses. Gases have masses. And the mass of all of those gas molecules in the atmosphere. Look up. Okay, you just see the ceiling. But I want you to imagine looking through the ceiling. 10 miles up. A stack the size of you, a cylinder roughly the size of you, of gases, 10 miles high, pushing down on your head, grinding you into the surface of the earth. Do you feel it? Do you feel like you're under pressure? If you spread out, it gets better. Why don't you feel it?
Because our bodies need it.
Why do our bodies need it?
So we don't explode.
Oh, there's that, yeah. Deep sea creatures have been notoriously hard to study because deep sea creatures, of course, they have evolved under conditions of much higher, they're under a lot more pressure than you people, let me tell you. Because they have not only 10 miles of atmosphere pushing down on them, but a couple miles of water, which is more dense. And so the things at the bottom of the ocean, the first people who attempted to observe like deep sea creatures, they would do this. And then you tell me what's wrong with this idea. They would catch them, and they would put them in a little container, and they would bring them up to the surface, and they would get them to the surface, and they would go, really, seriously, it was a bloody mess. Literally, a bloody mess. They would explode. You never heard that before? Oh my gosh, there are some fantastic images of early deep sea creatures. No. Well, that's a whole different matter, but, you know, take a dive class.
A similar occurrence happens when you take...
Because their bodies have evolved to have that external pressure holding them together. You have all evolved to have the external pressure of 10 miles of atmosphere pushing down on every inch of your body. If we take you to space, as my friend here observed, and you take off your spacesuit, which is pressurized to keep you together, you boil. Like there's no pressure holding your molecules together anymore. You just become a vapor. I'll let that sink in for a moment. You can think about that later today, or sadly at like 2 in the morning. It just makes me never want to leave the planet. I like this planet. It's a nice little planet. It's very good here. 10 miles of atmosphere and everything. So the atmosphere is exerting a force down on you, and the amount of force that it's exerting on everything, you, the desk, the floor, you know, other molecules, that's called atmospheric pressure. Okay? Because it's the pressure that the atmosphere is exerting on you. And at sea level, there's it's about 10 newtons per square centimeter. So you don't know what 10 newtons feels like. Let's get a spring scale. That 10 newtons per thumbnail size square, that's at sea level. If you're on the top of Mount Everest, and I want you to answer this with thumbs up or down, is the pressure on you greater or lesser? Okay, good. Universal agreement for those of you who are not too chicken to commit to a position. Yeah, because why? You're higher up, you have less than 10 miles of atmosphere pushing on you. On the top of Everest, you're about 6 miles high, so you've only got 4 miles of atmosphere pushing on you. Now, mind you, you're not getting big lungfuls of air, because the molecules are much more spread out, so every lungful of air has less oxygen in it, but there's less pressure on you. If you go to a location like Death Valley that's, I don't know, a couple hundred feet below sea level, is the pressure on you greater or lesser? Greater, yeah. There's more atmosphere pushing on you. So we tend to measure atmospheric pressure off of a sea level idea, and at what we normal atmospheric pressure at sea level we conveniently name 1 atmosphere. That's 1 atmosphere's worth of pressure. Now there are a couple other units of measurement we use for it. They'll become more important in the next chapter. Millimeters of mercury is one, and I'm going to tell you where that came from in a second. And the other one is, there's bars, kilobars, pascals, which I hate. But yeah, there are a bunch of different units of measurement for pressure. So the earliest barometer, a barometer is a device that measures atmospheric pressure. We can check the atmospheric pressure in here today. Briefly, the units for pressure are derived. It's not a direct measurement because it's force per unit area, so it's newtons per square meter, or atmospheres. And there's actually a table on 311 in your book. I would glance at it, but I wouldn't worry about it too much yet. That may be where we stop for today, which means we've done 0 math. Hold on. One last concept. So this is the concept of STP. Thanks. STP is standard temperature and pressure. It's also, some automotive thing. So STP is a way of comparing gases at an agreed upon pressure and temperature. And standard pressure is 1 atmosphere, standard temperature is 0 Celsius. Okay? So anytime you see STP, that tells you both the temperature and the pressure. We're going to start doing problems with STP on Monday. That's about all we got. So the next thing we're going to start is see if you remember how P, V, and T go together. When we change one, others change. We're going to start those on Monday. You'll have a quiz, FIP quiz on Tuesday. And then we'll basically wrap up, and we'll probably have a test, a quiz. It'll just be a big quiz on this chapter, like Wednesday of next week. So, because we're not going to do a whole lot of other stuff. Okay, we'll stop there.